All right, so welcome to chapter 16. There are 18 chapters in the book. We are very close. We're very close to the end. Very exciting. 17 is probably going to be one of the longer ones. Another, at least 3, I hope, lectures. We'll find out soon enough. But yeah, this one is about regression still. We're going to study it in a different light just to see like what could have gone wrong. How could it have been different? Because we were doing linear regression, trying to draw the best line between all the points, or among all the points of our data set, and it may look different if we got a different set of data. So we need to study the differences. All right, so please read chapter 16, and we will go from there. So yeah, here's kind of the idea. We want to do regression because we think that our data is arranged along a line, but it's never a perfect line, right? So when we're doing regression, kind of the goal or the idea or mental model, or actually the real mathematical model, is that really the points are on a line, but they got kicked away from it a little bit. Like we think that it's useful to have a line and that we can use that for predictions, but the data that we see in real life has been kicked away from the real line with some sort of normal distribution. Like centered at 0 is kind of the idea. We'll get to some words that say this, but you can imagine that when you take a sample from your population, you're picking points. Really, they would lie on this perfect line, but they've also been kicked away from it by like taking some points randomly on a normal distribution centered at 0. All right, it's like the distance of this dot from the real line, because like that's what represents the correlation perfectly between the x and the y variables. The distance from that true line, it's like we pretend or we imagine, we assume that it's taken from a normal distribution randomly with mean 0. And so like we just drew a random point and it happened to have been over here or something. Like, all right, there's like 3 away from the true line. Let's just like randomly. But on average, it will be 0 away. That's kind of the thought. It'll be 0 away from the true location. Like this one, we randomly take from our normal distribution, like, oh, it's like, I don't know, -2 or something. That one was started the true line, but was like kicked away by -2 units, where we drew that amount farther away from some normal distribution centered at 0. So on average, the points really are on the line, but they're a little noisy is the idea. All right, they're a little noisy, and we're assuming though that it's useful to draw a line, that there really is an underlying line there. Okay, but if you think about it, let's switch back and forth quickly between these two slides. If you think about what you really get, we don't get to see that true line ever, right? We can't take a sample of, well, it won't be a sample at that point. We can't take a census usually of what we want to care about. Like we want to take a sample over, or we care about like how all the people in the United States is going to vote. We're not going to go out and ask every single voter. That's not going to happen, right? So we're going to get a bunch of points, and they're not all the points. So we only get these dots. We don't get the true, real underlying line that they lie on. Okay, that's all we get. We get these dots only. And depending on how many we take, like the line that we're going to draw between them, right? Our best fit line, just like if we can imagine what that might look like, maybe something like that. I really don't know. Maybe that. I don't know. And that is a little bit different, right? It's a bit off from, you can imagine, like maybe it was something more like this. I don't know. Like that one down there is bringing it down or something. Like it's a little twisted from the real one, given our sample. And so we're not actually sure what the real line is, but we can get close to it with a good enough sample, with a big enough sample, right? So that's the goal, and that's the thought. We're never going to get this real line. So the question is, how far off are we from that real line when we do take a sample? That's the question of this chapter. All right. So here is the model, like the mathematical model for linear regression. So when we're trying to do linear regression and draw the best fit line and figure out its slope and figure out the intercept, we are assuming the following about our data. We're assuming, and this is why we want to use linear regression, we're assuming that the relation between the x's and the y's is perfectly linear. It really is a straight line. And I'll go to an example in just a second before I nail this home. The relation really is a straight line. We don't know what that line looks like, but we know it's there somewhere, and like the data is being sampled from that line secretly, kicked away by some normal distribution centered at offset of 0, but it really is on that line deep down, maybe a little bit off, but it's normal. It's centered at that line, okay? But normally distributed away from it, maybe a little bit. All right, so the relation is perfectly linear. It would be on a perfect line, but we don't know what that line is. And the scatter plot, the thing that we generate, our data, these dots that we get here, those dots are generated in that exact way that I was trying to say. All right, they're generated by taking points on the real line and pushing them up or down, like kicking them away randomly, according to some normal distribution with mean 0. So on average, it's perfectly on the line, 0 away from the line, not kicked away at all, but randomly kicked away. All right. So yeah, in that case, then, every point we get to see looks like this, right? This is how we think of all the points in our data set when we want to use linear regression. We think of them in this way, like, all right, the y is equal to, you start at, like, there's secretly a true line somewhere that we can't know fully. We can approximate it. Our y for every x is equal to, like, for this x. It's, you go and you get to the true height of that line, right? At that x variable, go to that spot, and then also kick it away a little bit. Some random error, maybe it goes up, and this is the real dot we get to see. So I'll draw that in, I don't know, rainbow. Like, this is the real dot we get to see. If only it was on the graph, right? It's just been kicked away randomly. There's some random error added to every point. That's what we're assuming. Okay, does that make enough sense? Any questions about that? It's you can make this mathematical, and I'm not going to really like test you on this idea, but that's how we're going to think about it. That's why we want to use linear regression. That's why it makes sense. There really is a line secretly deep down, and all the points, they would be on it if they could, but they've been kicked away a little bit by just randomly, but according to a normal distribution with 0 offset, with average 0 offset. Okay. That's what happens, and let me try to draw some examples of like how this line could be different. There's a cool simulation that your book did that I copied and pasted the code for that you do not have to understand, but here it is. Dun, dun, dun. So here's like an example of how regression estimates can differ from the truth. So you don't have to understand any of this. It's just drawing some examples of, it's making some sample error values. And it's drawing from, like the NumPy library can apparently create a random, like it can draw from a normal distribution with a certain mean and a certain standard deviation, most likely. And then here's what, I just want you to see the picture. All right, so here's the idea. So, okay, like this is the true line. Here are some points that have been generated in the exact way that we understand our model to look like these points, like this point really was started here, but was kicked away randomly that way. This point started here, but was kicked away randomly that way. All right, that's what we're assuming the data is generated by doing that. And so we just get to see these points, right? We just get those points only. That's our data set. And when we do regression, we have a formula that calculates the slope and the intersect of the best line that goes through these points, right? And then here is that regression line. You scroll back and forth. It's not quite the same. Okay, you see that? It's not quite the same as the one we get. And if I rerun this, it'll just be another random set of data, and the line could be even farther off. So here's like the true line. Here are a bunch of points on that line. Sometimes, like on average, like the mean is 0 for the error amount, or the offset amount from the true line. We're assuming that all the data is taken from points on the true line and then kicked up or down random. All right, that's what we get to see. It's like there's some variation in the universe. And so this one, we started here, it was kicked up. Okay. And so really we just get the points. We draw a regression line. We do the best that we can. This is the best line through those points, that it is the line, but it's never going to be exactly perfect. It's always going to be tilted a little bit in some direction. And in theory, it will never, I guess it could be parallel sometimes, but I guess usually it'll be off a little bit. And so there'll be like, it will intersect somewhere perfectly, but we never know where, which is kind of funny to think about. Does that idea make sense to us? Like that's the difference. We'll never get the true line, but we can approximate it. So that's kind of the goal of this chapter. So yeah, that's our model. We're assuming that the data was generated by taking points on the true line and pushing them up or down randomly according to a normal distribution with mean 0, and that's the explanation for why they weren't perfectly in a line. That's what they're using. Okay, so yeah, with that in mind, the question of the day then is, how far off could this line be? Could my regression line be from the true line? That's the question of this chapter. How tilted could it be? Like, Think about the slope, for example. How far off could the slope of my regression line be from the true slope of that true line? Okay? That's something we can figure out and come up with a confidence interval for. All right, that's the goal. That's predicting, regression prediction, regression inference. Okay, so here's the setup, right? We only get one sample. We worked really hard. We spent a lot of money on that one sample of all the people, whatever we got from them. All right. That's all we have. And so we know that if we resample, just like that simulation, if I ran it again, we get different lines, right? If we resample, we get a different a different piece of the population. We would get a different line that maybe wobbled in a different way, right? That's how it would look. You get different points. And so the question is, like, all right, we took this sample, maybe we got this line. We took this other sample. If we went out and did it all over again, spent even more money, we might have gotten that line. Who knows? The question is, if I took a census, like what's the real thing? What's the range that line could be within? Like the slope of it, for example, all right? How accurate is our regression line through our sample data? Because that's all we get, right? We don't get the real line. How close is it to that real line, okay? The one that describes the population perfectly, the total population perfectly. And so if you went and got another sample, you'd have another estimate, right? You'd have another slope, and like that would be, maybe we could average the two slopes or something and get a closer idea. And so if only, right, we had more samples, then we could compare one sample's line slope to the other sample's line slope and see like how much is it varying as I resample, as I take new samples. And so it's probably very expensive to go and take another sample, but we know a method that we can get another sample for free with, and it has to do with bootstrapping, right? So we have a friend who can help us. It is the idea of a bootstrap, right? So remember what that means. When you bootstrap, you sample the same amount of individuals from your from your sample. You take just as many. If there were 100 individuals in your original sample, then you're gonna take 100 samples again, right? You're gonna sample 100 times from that original sample. You take the same amount, but you sample with replacement this time. So you can maybe take a few more of the brown ones. You can take a few less of the blue ones, and so that simulates what the population might look like. Because maybe there's just randomly, it really did happen to there wasn't enough representation of the brown dots, and there was too much representation of the blue dots in the real population. So it's going to help us get more samples that look similar to the population still, but are yet different from our original sample. That's what bootstrapping is all about, right? So we're going to do that again. And if we do it enough times, we can get a confidence interval. Or like, all right, what's the range of the sample's slope, the regression line through that data? So that's kind of nice, right? We can bootstrap our sample data and get more of these dots, right? Different dots, which give us different lines if we do linear regression, and that will help us get more predictions of what is the slope, what is the intercept of that regression line. So we'd have a range now. It's like, all right, what's a 95% confidence interval for the slope of the regression line? Does that make sense? If we do that a bunch of times, we'd have a bunch of different values, and we want to see which ones we get more often. We can take a confidence interval in between everything. We can use our percentile function that we know and love now. Okay, so that's what we want, and I do it like, I don't know, 5,000 times, so you get a good enough approximation, right? And so you don't have to go out and spend a lot of money to get another sample. You can do the bootstrapping to get it done better. Okay, so that is called regression prediction. We want to estimate what we know. It's not going to be perfect when we get our sample. Like, what's a 95% confidence interval for the slope of the regression line? Something like that. That's what we care about now. And so let me copy and paste in a bunch of functions that we need. They're all from the previous chapter, more or less. Yeah, I think they all are. Yeah. So here are all the functions that we know and love. We've got convert an array of numbers into standard units, right? How far away from the average or the mean are the values, and then divide by the standard deviation. So how many standard deviations are all these values away from their means, from the mean of the values in that array? Standard units, correlation, we know you do an average of a multiplication of values and standard units land. So the slope, there's a formula using all that to get the slope of the regression line. There it is. There's a function that returns it, and then the intercept of the regression line. You call this function like this. You give your actual table and then the labels of the columns and as strings. I'll show you that in a second. And then fitted values is the idea of doing the prediction. So you got you give it the table, you give the x and the y, you want to use the x's to predict the y's. It's going to calculate the regression line, get the slope and the intercept. Maybe this should be an m, right? mx plus b. I like that better. mx plus b, so it's predicting all the original x values and seeing how far away they are from, and we can eventually see how far away they were. So given the x values, predict the y values. That's what fitted does. And then residuals is the error, right? You can create the fitted values, and then how far off it was from the real y column. That's your residual. It's the error away from it. All right, so those are all the functions we know and love. Let us import them so that we can use them. And the example for the day will be, let's do the mothers and the babies. That's what the book did. So here, I'll import that table of births. Here, bring this closer to me. New table. And then just to show you like the different values, let's do like a little sample. So here are different values from this table. And so you got like different, a decent range of all these values. Let's do, I guess the example that the book wants to do is let's try to use gestational days to predict the weight of the baby. So I think, I guess that's in ounces. Birth weight is in ounces and gestational days is in days. So how long the woman was pregnant for, and then what was the weight of the baby. We can use one usually to predict the other. You can imagine that if you were pregnant for longer, the baby has grown more. And so it's going to weigh more when it's born. So yeah, let's do a scatter plot just to see if there is a linear relationship, just to confirm that maybe this will work out. Gestational days, and then birth weight. And it looks like there's a decent line. Maybe some outliers, but it looks like it's going like that or something. So decent amount where like you spend more time pregnant, the baby's going to weigh more. So let's see what the correlation is, just to confirm. There is a line here. Is it a decent value? So it's the correlation for the births table of using gestational days and birth weight. How are those values correlated? Linearly correlated. That's what correlation gives back. That's like 0.41, so it's decently positively correlated. All right. They might be even more correlated if we get rid of these outliers, and that's what the book wanted to do just then. Apparently, this will be a better predictor if it's for like standard lengths of pregnancy. So apparently, according to the CDC, these are the numbers for preterm and post-term pregnancy amounts. So we want to cut off the values around those just to get like average amounts of pregnancy lengths. So preterm and post-term pregnancy cut-offs. So these values are just like neither preterm nor post-term, normal term, I guess. So 37 weeks is, anything less than that is apparently a preterm pregnancy, and anything over 42 weeks, and so these are values in days, is post-term pregnancy. So between that range, that's like a normal amount of time to be pregnant, I guess. So let's just consider those values. So I'll take births, and I'll replace the table with that, where the gestational days values are between. And that might give us a better prediction engine, where they're between 259 and 294, something like that. And then we can scatter again. Dun, dun, dun. So that looks a little bit more linearly related. You can see like it's going up a little bit, something like that. So yeah, let's see about the correlation there now. So I've changed the table, so I said births equals something. Let's do the correlation now. Is it any better? Oh, it's even worse. Oh, goodness. That's funny, actually. It looks like... Oh, no, they didn't actually do that. Excuse me, they didn't type these numbers. They typed different numbers. So let me read in the table again, just to get it back to how it was. And apparently, maybe that's just not enough of a range. What did they do? They did 225 days. So even less than that, to be all the way up to 325. So I guess they subtracted 25 days. And apparently, they cut off these guys, I guess. One's way over there. So, yeah, we went on both sides of that still. And that's the data set now. And the correlation of that is, I guess they played around with the numbers. I don't even know why we did this then. But yeah, we're trying to get rid of the outliers. So I guess we don't have to, I honestly don't see the point of that anymore. But the book did. Okay, so yeah, there. That's a better data set, and the correlation is a little bit better once we get rid of these outliers over here. Stuff like that, and maybe this one down here. So yeah, we're zooming in over here where the bulk of the data is. And so we get a better correlation if we just consider these values, and so we might as well go from there. And let's do that same scatter plot, but with the best fit line. So you can say fit line equals true for it to do it quickly for us. Dun, dun, dun. So there it is, and it looks like that's the line. That's the best line that goes through all these points, okay? And then the question is that the right line, right? So our goal now is, can we estimate the true relationship between the x's and the y's? Can we really find the true line that tells us how many gestational days gives us what birth weight? All right. So we can ask for, like, what is the slope? What's the slope? We have that function, right? If we scroll back up, I copied them all in. What is the slope of the best fit line? Takes the table and the two column labels. So of the births table, and it's always use gestational days to predict birth weight for this extended example. So the slope is apparently in normal units. You spend another day being pregnant, your baby gets about half an ounce heavier, 0.537. So cool, that's the value there. And now the question is, all right, how could that vary? If I had a different sample, how could that vary? And so let's do the bootstrap process to make a prediction, to make a confidence interval for maybe the slope of that line. Like we know for our sample, it was about 0.54 for a slope, but that could have been different if we had a different sample, right? It would have been different for sure. So let's try to see how far off it could have been if I had different values for my data set. So yeah, let's do that. Let me show it to you. What I will do is I will make an array called slopes, I guess. I'll make a blank array called slopes, and that will just bootstrap all this process. So we're going to store all the different slopes that we generate within this array. And then we'll go, let's say we want, I don't know, how many repetitions? They did 2,500. So let's do 2,500 repetitions. So randomly bootstrap 2,500 times a new sample. And let's keep track of all the slopes, all right? That's what we're going to do. So bootstrap, create 2,500 bootstrap samples, find the slopes for the best fit line between all those samples, and bring them all together, and I guess save them all in the slopes array. So yeah, for I in np.arange repetitions, so repetition the number of times, do the following. We would like to make a bootstrap sample from our original data, which is called births. And we want to do it with replacement. We want just as many with replacement, and that's actually the defaults for the sample operation on the births table. So that's perfect. I just say sample, and I got what I want. I've got a bootstrap sample now. They knew that's what we were going to want a lot, so they made that the default. So there's my next bootstrap sample. Let's get the slope of that bootstrap sample by saying, I don't know, we'll keep track of it in a variable. Bootstrap slope is, all right, give me the slope of, the slope function now, of not the births table, it's the bootstrap sample table now, but on the same x's and y's. again using gestational days to predict birth weight. So there's all my slopes, and there's the next slope, and I want to add that to my slopes array with the np.append. So slopes equals np.append. We know and love this process at this point, right? Append this new to slopes itself, this new slope, bootstrap slope. So there it is, and now I've got a bunch of slopes, and the idea is we would like a 95% confidence interval of what the true slope is. So this is going to be a giant array with 2,500 things in it. I'd like the 2.5th percentile, and I'd like the 97.5th percentile, so I can cut it off in the middle, and that's 95 in between. So that's what we want. So next we'll find the end points of the 95% confidence interval for the true slope. And bless you, we'll go from there. So this is like the left side is called percentile. We want the 2.5th percentile of the slopes, and the right side of that is the 97.5th percentile. If we're doing a 95% confidence interval, that is. There they are. So there's the two ends, and I guess the original slope, we can keep track of that, right? That's the observed slope. Observed slope is just the slope of the original table. We'll keep track of that might as well give that a name, right? So that's the slope of the regression line from the original sample. And we want to kind of see how it compares, all right? We want to see how that compares. So we can kind of print them out together, and this is what your book does. So let me just make it pretty quickly. It's essentially this, and I'll show it to you. That's just, you don't have to worry about this code, but we want to display the results, essentially. So boop. Let's make sure I'm not doing this wrong. Observe slope array. So yeah, this is going to make a table with all the slopes in it. It's going to give us a histogram, and it's going to draw just in a pretty way. You don't have to understand this, because I barely understand it. Between the endpoints of our 95% confidence interval, what the where the slopes that we generated lie. It's going to highlight that in yellow, and then it's going to print out our observed slope. It's going to round it to 3 decimal places for fun, I guess. And then it's going to print out the confidence interval, that's the left and right, that we've done. And I think I can run that now. Are there any questions about what that code's doing? You don't have to understand this last part. It's just printing it all out. But this part, do you see what's going on? We take a bunch of samples. We see what the slope should be in each of those samples, and we see how far off our sample was then from what we think is going to happen. All right. So it looks like our original slope was 0.538. That was our original slope of our regression line. But when we took a bunch of bootstrap samples, we took 2,500 of them, the slopes were different because we had different points at that point, right? And so a 95% confidence interval, let's print it out up here, it looks like we're getting, for the slope of the real line, we're 95% confident, given the simulations that we've done, given our bootstrap sampling, that the slope is between 0.458 and 0.617. All right, so you see that it could range quite a bit. It could range a decent amount, like over an ounce per day, depending. So that gives us a good guarantee, though, that it is a positive relationship still, but we can't just go saying that it's going to be 0.538 all the time. We're not sure if that was the best answer. We know that we're 95% confident the real answer is between here. That's how we can say it. All right, so our data maybe wasn't the right answer, but we can use that to generate a confidence interval for where the right answer probably is. Okay, and I guess that's the moral of this story. Are there any questions about that? And I just drew a pretty picture of that. Cool. Let's see, am I going to use that ever again? Let me search something real quick. Because one thing they did, and I might as well show it to you, it's pretty cool. interval. I guess we are going to use that eventually. So let's turn this idea, this process, into a function. It's a cool, kind of a cool idea. So here, I'm going to take all of this. I'm going to turn it into a function. I'm going to show you how. All right. So I'm going to say def instead. Def bootstrap slope interval. Because what this did was it predicted the slope using bootstrap sampling. So I'm going to take all this. I'm going to indent it. If you highlight it all and press tab, it indents everything for you. And then I'm going to say, all right, you give me a table called T, you give me an X column called X, you give me a Y column called Y. And honestly, we can make the repetitions also be a parameter. Tell me how many repetitions you want to do. Do you want it more precise or less precise? And we can also give a default value. I'm not sure if I've ever shown this before, but this is how you give default values when you're making functions. If you do not give a fourth argument to this function when you call it, it's going to have repetitions exist and be this default 2500. But if you give a different value, like you give 5000, then it would look a little different. All right, so let me change this all in that way, and I'll show you. So dun, dun, dun. That's what it's going to do. And yeah, let me walk you through it. So we're using the table called T now. It's not births anymore. Like whatever table you wanted to use. We're using a table called T to start. We're sampling from that. We're getting the slope of the bootstrap sample, and we're using the X and the Y column that you passed along. It doesn't have to be gestational days and birth weight. It's whatever the X and the Y was that you wanted to use. See how we can generalize that and make this work for a lot of people now? X and Y, X and Y, and yeah, we can get the slope of the original table, a table called T, right? So whatever we were passed, whatever that table was. And let's see, do I have anything that says births anymore? I don't think so. So yeah, this is now generic. It's like for that table that you wanted to get the slope interval for, make some samples. We're going to use the X to predict the Y, get all the slopes, keep track of them. You see how we generalize what we just did. That's kind of neat. And so the way you can call this to do the same thing now is you say bootstrap slope interval. Oh, I have to press play to make that be concrete. Bootstrap slope interval on the births table using gestational days to predict birth weight. Just like that. And if I don't give anything, I can run this right now, even though there's a fourth thing. That's what this equals sign means. If you did not place something right here, right after the name of the column, if you don't put anything there, it will just have 2500 be the default value for your repetitions variable parameter. But if I gave like 5000 here, that would override the default. Does that kind of make sense? That's what would happen. And so we can keep the default, that's fine. Or we can say 3000, I don't know. But if you didn't give something there, it would have done the default 2500. So here, let's run it. Let's make sure it works. But now this will work for any table. Any table you want to pass, give me the X, give me the Y, it will calculate the bootstrap slope interval for it. And so, yeah, do we get about the same value? 458 to 617, 459 to 618. Oh man. So we did more samples this time. We got a different kind of interval. So that was maybe more precise. I'm not sure. So yeah, did we see how we could turn this idea into a function, and now we can pass any table, any X column, any Y column. It's wonderful. Very, very nice and generic and useful for us. All right, so there's that. You can predict the slope, like a confidence interval for the slope. You could predict a confidence interval for the intercept, and you could draw like what that might look like, all the different ranges. That'll be cool. You can also use a confidence interval to predict the prediction. I will tell you what I mean by that. So this is kind of interesting. So let's say, let's go back to the original thing. Like we've got all this data, right? And let's say, let's pick 300 days as a good example. So like if, let's say we've got another mother that we know she's been pregnant for 300 days exactly. Or we think that's her due date or something. And so we can go looking on this line and use that as a prediction, right? A regression line, and use that as a prediction for how heavy the baby is going to be. But do you see how we have a bunch of data for 300 days and it ranges a lot? So we're not actually sure, like it's not perfectly on this line. It might be off a little bit. So let's give a confidence interval. Let's try to create a confidence interval for that for 300 days. If somebody was pregnant for 300 days, what's a 95% confidence interval for the weight of that child? Does that make sense what we'd like to do? you can use regression for that in the same exact way. You take the bootstrap samples, you come up with the right line, you see what the prediction should be. All right, you see what the prediction should be. So that's kind of neat. All right, so let me write that in comment land. So what we'd like to do is we like to predict, right? We predict a confidence interval for someone who's not in our sample. That's the idea. Someone who's not in our sample, we want to use regression for it. All right, so that's our goal. Using linear regression because we think that the data is linearly correlated. So what we do is we do have data, right? We have data for 300 gestational days, but it's all over the place, right? It's up and down. It's all over the place. We don't have everybody agreeing on how heavy the baby weighs if the mother was pregnant for 300 days. So, but it's all over the place. And also only for the people in our sample. They were specific people, right? And only for the people in our sample. And so what we can do then is what we should do is then let's do a bootstrap. Let's use the bootstrap process to see how our prediction could have changed. How the prediction changes for how regression is going to think the baby is going to weigh at exactly 300 days. Okay, does that goal make sense? Because when you take a bootstrap sample, you're going to get a bunch of different dots, and those dots will wiggle the line, and we can see what that line says at 300 days. Does that make sense? We do that enough, we got a confidence interval of the prediction now, and that's better than just one, just for our original data. Because we know it's going to wobble. It depends on our sample, and we can't sample everybody. So that's pretty cool. Yeah, let's make a function to do that. All right, so I'll make a function that's helpful for this. Let's make a helper function that's like prediction at, I think is what the book called it. That's not something we have, right? No. So let me show that to you. It's called, let's make this function right here, and I'll explain it. Prediction, this will be helpful for us when we do our sampling. Let's see. Is that how I want to do this right now? Maybe. We'll find out. So yeah, let's do that. Prediction at. So give me a table, give me an x column, give me a y column, give me an x value that you want to give me the prediction at. All right, so let's do a doc string for this. Finally, we barely ever do this, but let's remind ourselves what's going on here. So T is the table we would like to make a prediction with. X is the label of the x column. Y is the label of the y column. And then x value is going to be the x value that we want to use to predict the y. All right, the x value for which we want to predict y. It's like we got a new person. What does regression tell us that the y value should be? So that's just, what do we return? It's just create the line and go to that x value point on the line and see what the y was. So it's like, it's y equals mx plus b. So go to the slope for that table, use the x's to predict the y. So there's the slope, there's your m times the x value plus b, the intercept of t, x, y. This function kind of makes sense. Just like create the regression line for this table in x column and y column, and then go to this x value and tell me what the answer was. Tell me what the prediction was. Prediction at. So there it is. And we can say prediction at 300. For the births table, using gestational days to predict birth weight, which I will be copying and pasting. Give me the value at like 300 days. That's what I want. And there it is. That's apparently our prediction for our current data. We're saying that, all right, if you were pregnant for 300 days, the birth weight is going to be about right here, which is 130.8 ounces. Okay? So that is prediction at 300, let's call it. So I just made the function to helpfully get us that prediction at a certain time, a certain value. And yeah, we can go from there. So, oh, there's a cute little picture that your book drew. Again, you don't have to understand this, but here's that picture. Dun, dun, dun. Don't worry about any of this code, but this is just a cute little picture that does that. It's like, all right, here's 300 days, here's the line, and you can see exactly where all the things are. Was that necessary? I'm not sure. But the question now is, like, how would it have been different? All right, let me show that to you. This is code you do not have to understand at all. So, like, none of this matters. Let me show that to you. So let's say different bootstrap samples will give different estimates. Let me prove that to you graphically, all right? This is like a visual example. So like here's our original one, 300 days, it was that. And then here's some code that they made in your book that's really cool. And then I'll show you some more code that's really cool. You don't have to understand any of this, all right? So this just creates 5 bootstrap samples to show you, like, all right, here is our original sample, and here is what 5 different bootstrap samples look like. Do you see how they're slightly different? Like this one went dot, 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 2 dots. This one went dot, dot, 1 dot. See it? So it's a little bit different, but generally the same. It's supposed to look similar to the original sample, and yet it helps you understand the original population better because it's still varying. And so that's what the different bootstrap samples will look like. You got 5 different ones. You can then use all of your samples, use your different bootstrap samples to make predictions at a certain point. So here's this one. Again, you don't have to understand any of this code. It's just making a pretty picture to prove a point. So at x value of 300, this one took 10 bootstrap samples and made predictions from each of them. Here are all the regression lines for 10 different bootstrap samples. And here they are at x equals 300 predicting 10 different things. You see that? And so that's what we want to do. We want to collect all the different predictions at this value that we care about and then make a confidence interval. That'll give us a much better idea of where the real answer lies, what the best prediction is. 95% of the time, you're going to have a baby between this weight and this weight if you've been pregnant for 300 days exactly. That's what we would like to calculate. All right, assuming that the data is linearly correlated. That's our underlying assumption here, because we're assuming that we can use regression, so we have to assume that this model describes our data exactly, which may or may not be true. But we had like a 0.4 regression value. It's decent. All right. So that's what we're doing. All right. That's what's going on. And this little example calculated a lines table that I can just show you. Like here's the numerical differences. It was like, all right, these are the different for the bootstrap samples that we randomly generated 10 of them. It was like, here's the slope and intercepts for all of them. And here was the prediction at x equals 300. So it's just a numerical example of what this picture is showing. Right, they're going to be all over the place, and that's good because that's going to help us create a confidence interval for what it should be. How far off are they each time? So yeah, let's go from that and make now a wonderful little function. So let's see, how do I want to do that? I think that this is the right time for it. So just like we made, I'm eventually going to have you do something. Give me a second. Got to get through all this stuff first. I'd like to do the same kind of thing that we did here. Let's make a generic function that takes a table. Let's work on it this way and not be specific anymore. Let's make a generic function that took a table, an x column, and a y, where we wanted to use the x's to predict the y's. We could also give it a number of repetitions again. And let's have it do not a bootstrap slope interval, but like a bootstrap prediction interval for an x value. All right? That's what we'd like. So let's make that function. All right, so let's do def bootstrap prediction. So give me a table. Let's call it table this time. I don't know. Give me an x column. Give me a y column. Give me a value that you want to look at, like an x value that you want to make a prediction for, and give me a number of repetitions. Maybe we can force the user to give me a certain number every time. We won't say equals this time. That's what we want. And so just in general, like we're about to fill in this function. What does this all mean again? It's like, all right, we would like to make a bootstrap prediction of the variable y, like the y column, whatever we pass along, at the x value, whatever that is. All right. And we pretend that this is a brand new value that we've never seen before. Like it's a value of a new individual. So we can call this new x maybe. That might be better. This is the new x value that I'm seeing. Like I've got data for that value, but I'm not sure. It's not perfect, right? It's all over the place. Let's come up with a confidence interval. All right. So yeah, the data is contained in the table called table, and we want to make predictions using linear regression. Prediction by regression of y based on x, and then repetitions, just to spell it all out, we could have done a docstring, I guess. Repetitions is equal to the number of bootstrap samples, or replications is what your book says sometimes. So I wrote that down. Replications of the original scatter plot. All right, the original sample, really. But you can think of it as that scatter plot that describes it. So, all right. Again, we want to do the same process that we did up here in this function. We want to take repetitions many samples, and this time the thing that we're keeping track of, the value of interest, is not the slope. It's going to be the predicted value at that x value we cared about, like 300 days, something like that. So that's what's going to change here. And so I could take a lot of this, honestly. I'm going to copy and paste all this, and we're going to change it as necessary. All right. Boop. And it's called table now, too, so that's going to be a little bit different. So, all right. Dun, dun, dun. So for each repetition, what are we doing? We are, I'll zoom in over here, indent. We want to bootstrap the scatter plot, bootstrap the data again, like make a new scatter plot. Think of it that way. Get the prediction, right? Get the prediction from regression, the regression prediction at that value, at that new x value. And then finally, add to the list of all our predictions. So we'll call this predictions. How about that? And that's a good way to start. So predictions, add to predictions. And so, yeah, we've called it table now. We're going to take a sample from the table called table, called it differently. We want to go that many predictions every time we take a bootstrap sample. We're not going to get the slope this time. We're going to get a prediction at this new x value. Bootstrap prediction, let's say. All right, so we're going to use this nice function that we made for ourselves right here. It's prediction at. Yeah, that's what we need. Takes the table, the x, the y column labels, and then the x value that we want to make a prediction at, which is going to be our new x. So there's a lot going on here, I know, but we're getting there. There's a lot of moving parts to this idea. Prediction at the bootstrap sample table for the x and the y columns at this new value called new x. This thing that this individual's value, this x value, for an individual I'd like to make a prediction for. It's not part of the original sample, that's why we're saying new. And then my predictions add to the end of it that new bootstrapped prediction. Okay. And now it's predictions that we want to find a 95% confidence interval for. So there they are. That's for the, what do we say here? Find the endpoints at 95% confidence interval for the predictions, I guess. For the prediction. The true prediction, I guess. And then, yeah, we have the original or observed prediction, we could say. That's our original data. How did it predict that new x? Because it's some dots. We drew a line for those dots. Well, what was it saying for 300 days? It was 120 something, I guess, if I remember. And then, yeah, let's call this, it's predictions now as the table's name, which doesn't really matter. Make a histogram. We want to, I guess we can give it a label. X label, predictions at You don't have to understand any of this code down here. Plus stir mu x. And then we want to still go from left to right, still do yellow, still do all that. This is not the slope anymore. This is the height of the regression lines, the y values. Line at x equals this new x value. You can say plus to add a string to a string. Turn new x into a string. Put it there, and then it's going to be original. It's the original height. You can round it, sure. That's still fine. And the 95% confidence interval for the prediction, right? Let's just say 95% confidence interval. There we go. Yeah, left and right, rounded to the nearest 3 decimal places for fun. And I think that is a good function. Are there any questions about what I did? Again, do not have to understand any of this code down here. But what we did is the same process. We want to make a bunch of predictions at that value we cared about, like 300. Something like that. Do that a bunch of times and calculate a 95% confidence interval for it. And so here's how you would call this function. Sorry, it's going to have to be like at the very bottom. So showing the original, you say bootstrap prediction. Give me the table's name, so births. Give me the x and the y, so gestational days, birth weight. Don't worry too much about all that. We just got to copy and paste. And then we need to give an x value that we care about predicting at. Let's do 300 days. And then repetitions, I don't know. Let's do 2,500, so we don't have all day. The more you do, the better approximation you get, of course, but it's already slow. Oh, goodness. Okay, so I forgot to say something was still t, but it's now I've called it table, just to show you that it's got to be precise. Prediction at table. Do that. Was it that line? Originally, yeah. So I think that would have worked had I changed that to table instead of t. And then let's do it again. Hey, there we go. All right. Here it is. What did I want to say? I forgot a little colon there. Where should I be putting that? Plus a colon. So that's fine. So the height of the regression line at x equals 300 was 130.81. So that was the original value for our original sample. It was 130 days was our prediction. But now, when we took 2,500 bootstrap samples, the height of the regression line at x equals 300 was as low as, in the 2.5th percentile, about 129, all the way up to 132.7-ish. And so that, we can say, that's our 95%. There's a 95% chance that the height of the regression line at x equals 300, like this is the prediction that line would have given us. And that's how it ranges. 95% of the time, we're going to see that. That's what we can claim now. All right. Are there any questions about that? Does that kind of make sense, what just happened? There's a lot of moving parts, of course. A lot of code there. But I hope you see the logical progression. That's all I really care about. You can go looking up this code later. But yeah, that's we got a confidence interval now. And a cool idea, a cool fact is let's do another prediction for another amount of days, which they have chosen to be more towards the middle. Like the middle of this is like, I think that they're all clustered around 280 or so for x. Like let's go to like 285. Let's look at the same interval for 285 days. And see if we notice something. Because this value is closer to the average of like the original births table. Like give me the mean of the births column for gestational days. Like what is the average amount of gestational days for our data set right now? It's about 280. So here's a value very close to the mean. And do you see how the confidence interval, the range of it, this was what? 29, 30, 31, 32, like 3.5. This one was more like 2. The distance was shorter for this interval. You see that? If you subtract the ends of this interval for 300, which is farther away from the mean of the data, it was a bit wider than the interval for 285 days, which was closer to the average of gestational days. So we saw this was a tighter bound, interestingly enough. I guess one way to explain that is we had more data around the mean, because all the values are clustering around there. That's one way to say it. Also, if you go back to the idea of how regression works, secretly the formulas for like the slope are all involving the mean secretly. Like they're centered in standard units land at 0, 0, which is the mean of the x values and the y values. So that's cool to think about. And so the line's just going to kind of tilt around that, and that's not going to change too much when you take bootstrap samples. So that's kind of interesting in itself, and I can draw you a cool picture to show you that. Oh wait, not this one, but this one. Whee. And then I can give you some things to try. So now I've shown you a lot of things. I'll give you all this code. So this, again, don't have to worry about any of this code. Don't worry what it's trying to do here. But it's just showing that when you make predictions using bootstrap samples, when your prediction is closer to the average, closer to the mean of the x values, it's going to be closer. Like the interval is not going to be as wide as it is for the other values. And this happens. This is random, so it's even different this time. But this is kind of the idea. Here is a prediction at 285. We took, this is making 10 bootstrap samples and making predictions at y equals 285, or x equals 285, and this is making 10 predictions at x equals 300. And you see how they're kind of all centered around the original mean of the sample. The original samples. When you take a bootstrap sample, the mean's not going to change too much. And so that's where the line is being centered, more or less. That's where it's pivoting. And so you haven't wiggled as far when you're close to the mean. It's kind of the idea. So your interval is going to be a bit more, it's going to be tighter, I would say. And I hope you see that. This is all under the assumption that our data is linearly correlated, though. We have to remember that. Like, does it follow the model? But if it does, like this is why we see this effect. Okay, so yeah, moral of this story: predictions closer to the mean have less spread than predictions farther away from the mean, and this is why. I think that's what I wanted to say. Are there any questions about any of that? There's a lot of data all at once, but the idea is use bootstrap samples to predict regression stuff, slopes, intercepts, predictions at a certain variable's value, stuff like that. That's what we can use bootstrap sampling for now, to get confidence intervals. Yeah? So with that, I want to give you all this code right now. So that you can go to the code from class for like last time or something and like look at it, because I want you to try something. Now the time is all yours, for at least a second. So if you refresh the code from class page, you should now have access to a chapter 16 file, and you can go looking at that on our GitHub page. And what I'd like you to do is do this one. So I got two examples, but let's start small. So try to get the son's heights table, because we were using father's height, right? Of what was it? Son versus father. So use the father's height to predict the son, right? Get the bootstrap slope. Let me just write that out better. Use father's height to predict son's height. Get the bootstrap the slope of the regression line, and get a 95% confidence interval for that slope. Does that idea make sense? So what I'd like you to try now is kind of the same thing that we just did. Use the father's height to predict the son's height. Do a bootstrap sample, it's like 2,500 of them again. Try to bootstrap the slope of the regression line and get a 95% confidence interval for it. All right. It would be helpful if you did not just copy and paste this function, because it's really you just using this function, right? You could, I guess, you could use this function, but I would like maybe use it at the start to see what's going on, and then try to do it yourself. Try to like copy and paste this, change the name of the table to the right name of the table, do the percentile, like type it out, because that's how we get muscle memory in our brain as well. All right, and then compare that to the original slope. But yeah, you can use this function at the very end to like try it all over again and draw a pretty picture for you. But it's essentially you're doing the stuff of this function. Does that make sense? So yeah, give that a try for a few minutes, and then we'll take a look. And go from there. I have one more example with cereal, and then I want you to try. But yeah, I'll give you like 4 minutes to play around with this one. But I want to drag in the sun's height file. I forget the name of the function already. Bootstrap slope. Bootstrap slope, something like that. And remember how to interpret that slope as well. It's going to be like, it's inches, right? Those are I think that's the unit. So like, you get a slope of 0.5, that means with a father's height of increasing by 1 inch, then the son's height increases by half an inch. Okay. Mm-hmm. All right, that is my timer. Let's try. Well, I guess I just have to call the function, but there's a lot of importing stuff on your end. Well, let's see. Let's see how much the father's, or how much the slope of using that prediction for father's height to predict son's height, how that changes. So I don't know, son's heights equals table, read table, son's heights So there's what it looks like. We want to use father to predict son because we saw that that had the best correlation. So honestly, you would have done something like this. Oops. Where are we? We want bootstrap prediction of that table, but we want to make an array of a bunch of, we're going to take a sample of the table a bunch of times, son's heights, 2,500 times, let's say, and, oh, sorry, that's prediction. We want to take 2,500 samples maybe, bootstrap samples, so draw with replacement, and the same number of individuals as was in the original sample. Give me that slope for that bootstrap sample, keep track of all of them, and do a 95% confidence interval using the percentile function. Right, so we've called it bootstrap slope interval. I can keep the default of 2,500 repetitions by just not saying anything for the fourth argument. So for son's heights this time, using father to predict son, father on the x, son on the y, and then I can just close that and say 2,500. So it looks like a 95% confidence interval is decently wide for how this kind of is working. For our original data, it was about 0.5 exactly, which is kind of funny. So the father is an inch taller means the son's going to get half an inch taller, regressing towards the mean. It's the original definition of regression. And yeah, it looks like 95% confidence interval is pretty wide. It's from around 0.37. So the father gets an inch taller. That means the son will only get 0.37 inches taller, versus all the way up to, if the father gets 1 inch taller, the son maybe gets 0.65 inches taller, 0.646 inches taller. And so that's our range of, assuming this really behaves linearly, that's what the slope of the regression line should be. We're 95% confident that's between there and there. And so we can then gather ideas about that. Think about what that means to us. But yeah, are there any questions about how we do that process? Would you do it without the function call? Yeah, because I would like you to try one more thing. Let's do serial. And now you're forced to not use the function calls, because what I'd like you to do for serial, let me read that in real quick. Serial. Now I want you to extrapolate with your brain. Here's the serial table. We got a bunch of, not a lot of serials, honestly. And we got all these different values, and we noticed that the correlation of, what was it? Potassium and fiber was like insane. Potassium and fiber. And let's do fiber on the x, I think is what the correlation doesn't matter for that, but let's do fiber on the x. I think that's what I wanted to try. So the correlation was very good. And so let's see, is that just like due to chance? Maybe. Like where does the correlation value lie? Because that's another thing you can bootstrap, right? It's due to the data. We can get another sample and the correlation value will change, won't it? So I would like you to try the following. Bootstrap correlation of, it's always potassium versus fiber. But the order doesn't matter for correlation because it's just, you call it and it does it. It's just multiplying things, right? In standard units land. So what I'd like you to try is the following. So try to get a 99% confidence interval this time for the correlation value for potassium and fiber. Does that idea make sense? So you're going to have to take, I don't know, 2,500 samples again. There is no function that will do this for you right now, but you can look at our other ones. Look at our bootstrap prediction example. Honestly, going back to the original before we bootstrap slope interval function, before we even made the function, maybe this one, this cell right here is the best one to be looking at, because that's kind of when we did something ourselves manually, because that's kind of what you want here. You want to make an array that starts out empty and add to it like every time you take a sample of your serial data set this time, go and get the correlation value for that bootstrap sample. Does that make sense? Like that's the new thing. That's what changes. Go and get the correlation value and give that a try. All right. Do a 99% confidence interval for that. And then if you finish, you can use the function for the last one just because we're running out of time, but try to do a 95% confidence interval as well for the prediction of like using fiber to predict potassium when fiber is equal to 5 grams or whatever. what is a 95% confidence interval for the level of potassium that should be in that cereal? That the linear regression model would predict, at least. So try the two. This first bullet, second bullet really, is going to be the more involved one, because you're going to have to do it from scratch, right? Blank array, 2,500 repetitions is so fine. Do more if it's powerful. And then you want a 99% confidence interval value, confidence interval of the correlation values. So you can say I'm 99% confident of the correlation between the potassium and fiber found in the cereals that were available in 1989 or whenever this data set was made. The correlation is between here and here. Weird. Interesting. Another minute or so to try it, and then I'll do it too. All right, that was my timer. Did any questions come up as we were trying it? Did it kind of make sense? All right, let's do it. Potassium and fiber. Let's see. Was that a fluke that it was 0.9? I guess it depends. It was a very small sample, honestly. Only like 77 cereals. But maybe that's all there was back then. Who knows? I would like to probably copy and paste this function, because I can just change out the t for the table that I care about. Same with the x's and the y's. Let's do this. I think that would make the most sense to me. It's got to be 99%. And correlation, but not slope. So let's go from here. Let's do 2,500 bootstrap samples, find the correlations, and save them all. So I'll call it correlations, I guess. Correlations, bootstrap, correlations, append, bootstrap correlation. Wait a second, now I've forgotten how to spell correlation. There's 2 R's and 1 L. Boop. There we go. Correlation, where we take, the first name of the table is called cereal. So make a bootstrap sample of the cereal table, give me the correlation, boop, of the bootstrap sample with the x and the y's could be either one in any order, because correlation doesn't matter. Fiber and potassium. And then add that bootstrap correlation value to my array, and I want a 99% confidence interval this time. That was my goal for us, and so I want to go between 0.5 and 99.5, right? There's my window. And the observed correlation, I guess we have that too. It's up there. I don't have to do this. That's the 0.90. But our left and right will tell us, if I put them together, our 99% confidence interval for not the true slope, for the true correlation, with 2 R's and 1 L. Interesting. Is that just going to vary so widely? Or did I do something wrong? Cereal, bootstrap sample. Cool. Fiber, potassium. That is not even, it doesn't even hold our original value. Did I do something wrong, or did you guys get that too? Oh yeah, sorry, slopes. I said slopes here still. It's correlations. I was gonna say, what is happening? There we go. There we go, that makes more sense to me. All right, so it looks like we're 99% confident that the correlation could be as low as 0.84 or even as high as 0.95. Interesting. And so it's decently high still. It's ridiculously high, which is exciting and interesting. But there is a decently wide range. It's like 10% difference in correlation value. But that is still interesting. And so that's a number that we care about. We know that it's still high with a 99% confidence interval. It's like above 80.8. And that is very, very correlated still. Yeah. And then for the other one, prediction of potassium versus fiber when fiber is equal to 5, 95% confidence interval. You can do it from scratch, or you can just call our function, because we were using 95% for that one. Bootstrap prediction. Bootstrap prediction of our cereal table, where we were doing fiber to predict potassium in that order. And then how many repetitions? We'll do 2,500. So we had to give that one there. Oh, did I do that? Oh, sorry. For a value where the fiber was 5, so 5 is the x value. We care about the new x value. 2,500 repetitions. It looks like we're 95% confident that when we do it, I need to fix that. I thought I put a colon. I did, but I never said play again. Aha. Again, do it again. It will bother me otherwise. There we go, x equals 5 colon. The original height of the regression line, so like you had 5 grams of fiber, 173 milligrams, something like that, of potassium, micrograms, I really am not sure. And then for our 95% confidence interval, we noticed that it could be as low as for 5 grams of fiber, you can have 159-ish units up to 197-ish units of potassium. Still a large amount, still very correlated. Yeah, so that's something that we can extract from our data now. Again, assuming that it was linearly correlated. That was our underlying assumption for all of this. If it was not linearly correlated, kind of all this goes out the window. But still a decent predictor, right? But it's not perfect anymore. Yeah, any questions about these? Yeah.
Curiosity. So I graphed both of them, and the correlations table looked like it was skewed from the left. And the predictions is skewed the opposite way.
Oh, nice. The predictions was skewed in the other direction? You'll have to show me. So you did, what kind of graph did you do?
I just copied and pasted the stuff and changed the groups.
Oh, so you made this, oh, I see what you mean. Yeah, let's do a histogram real quick. I think that would be interesting. Dun, dun, dun. I don't know if I know the answer, but we can at least try here. We'll do this little table stuff. Because I want to know, at least we can see. So our predictions, let's get rid of this label, it doesn't matter as much. It was correlations. Predicting correlation, I guess correlations. And I spelled correlations wrong there, and I need to fix it in my mind. There. Did I fix it everywhere? Yeah, just do it again. And then I'll work on this. Left, right, sure. It wasn't the height of the regression line. It was like the original correlation. We know that's 0.90. We don't have to show that anymore. And then approximate interval was there to there. Yeah, let's do that. Oh, you see, that kind of skew is what you saw? Interesting. It looks like my guess for this is that there are some serial there are not a lot of serials in this data set. It's less than 100. If we needed thousands to have like a decent looking graph. So I think there's like one serial with probably, or a decent number of serials maybe with not a lot of potassium and not a lot of fiber or something like that. Mm-hmm. And like when you did your bootstrap sample, like it duplicated those a little bit more often or something. That's my guess. But again, it's random. I guess it's more likely to get a bunch of weird serials with, like, you've excluded all the ones that were healthy or something in your small bootstrap sample because it's only less than 100 serials. I think it has to do with the sample size in my mind, but I could be wrong. Yeah, that's a great question. A great thought. Yeah, any other thoughts, ideas? Nice. What else could we do there to think about that? No, it's a different value. It could be that the whole... What's the scatter plot look like? How about, let's look at fiber. Like, is fiber in the serial? Let's do a histogram of just that. I think that would help us here.
I guess it could make sense because it's saying that it could have lower correlations and the correlations have lower potassium values.
Yeah, that would make sense. Yeah. I guess it's usually, there's not a lot of serials with a ton of fiber. Okay. So the second you sample a couple of these, then you've just shifted your graph over quite a bit, maybe. So like these are outliers in a sense. I could see that being a thing. That would make sense to me. But yeah, I'm sure there's a bunch of competing ideas, but that's a great thought. That's like that warrants further investigation, at least. Very nice. Yeah, other ideas, other thoughts. Cool. The last thing I want to talk about, just one more slide, is there's the question now of like, if the correlation function gives us back some values, like weakly correlated, 0.2 or something, like what are the odds that it was just due to the data? Like what if we know how to do a confidence interval now? Like what is the likelihood that the correlation was 0. Like there was no correlation at all between our data values. And like we just happened to see something that was not 0 due to random chance, due to the sample that we took. We could have taken another sample and saw no pattern at all. All right, so what are the odds that we saw just a pattern out of nothing, out of mist? So you can do a 95% confidence interval, and then you have a hypothesis test at that point. Like your null hypothesis, like the slope of the true line is 0. Your alternative would be the opposite of that. Like, no, it's not just 0. It's something else. It's something that's really correlated positively or negatively. And you could use a 95% confidence interval to be 95% correct of which of these you choose, if that makes sense. And so I'll just copy and paste some code because we're running out of time. But the idea is, like, what if the line is flat and there's no association at all? Question marks. That is a possibility. So we have this original function that I'm not going to tell you much about. Here's an example call to it. An interval of that sample size 25, let's say. So here's a silly example where the true line is 0. And these are the data points that you get from that true line by like swaying them up and down by a normal distribution, centered at 0 though. Well, how far are you kicking it? And then you get to see the dots only, and you get your regression line has a non-zero slope at that point. Like, what are the odds? Well, that's what you see, right? When you do that again, it may be more or less pronounced. Line, dots. That line is even more increasing this time. Like, what are the odds you thought there was a weak correlation and there just wasn't one at all? So you can use a bootstrap sample to get that. A good example of something that probably has no correlation at all is for a births table. You got the maternal age, the age of the mother, and the weight of the baby. And let's do a fit line equals true this time. Look at that. That's a slightly increasing line. Slightly increasing line. We can get the slope of that in just a second. But I think you can imagine that the age of the mother doesn't really affect the weight of the baby. It's not really a thing, but maybe if the mother's older, there's a slight like increase. Like, look at the slope for births of the regression line, maternal age, birth weight. It's like, all right, if the mother was 1 year older, the baby is going to weigh about 0.1 ounces more. Like, we're getting that from our data, technically. We should probably check that, right? Is this really true or is it not? So what we can do is we can make like a 95% confidence interval of the slope of this line and see if 0 is anywhere in that interval. And if it is, that means that probably we don't reject the null hypothesis. Like, really, probably the slope is, almost certainly is true, that it is 0. There's no correlation at all that we can infer anything about. So bootstrap slope interval for this table and this x to predict that y. And so if we do that, it's random every time, but we should see that 0 is contained within a 95% confidence interval. It's like, all right, if we do 2,500 bootstrap samples, the data set slope gives us that, like 0.1, but for a confidence interval, we're 95% confident that the true slope of the best fit line could be negative all the way to 0.3-ish, negative 0.1 to positive 0.3. And so 0 is contained within that, which would tell us that probably there is a decent chance, a 95% chance, right, that it could have been 0, right? Or there's a 5% chance that it was non-zero. You can think of it that way. Something like that. It was not contained within this. So 0 is, I think I was wrong in what I just said, but I think you get the idea. 0 is contained within a 95% confidence interval. We were 95% confident that the slopes of the regression line are between there, and 0 is contained within that, and so that would mean that it is quite likely for the slope of the true regression line to be 0, and so we should not be going and rejecting this null hypothesis. There's a good chance that there is no correlation between age and birth weight. All right. And so that's something you would want to check if you had a very small correlation value, like maybe this isn't what to be reaching for. You can't use one to predict the other sometimes. So yeah, we've used examples where you can use one to predict the other. Sometimes that just doesn't work. Okay, you can't use everything to predict everything else. Yeah, I think that's the moral of that story. That's where I want to leave us. Are there any questions about any of that? All right. There is one assignment that depends on this chapter, and that was it for it. So yeah, it looks like we needed for homework 11, we needed chapter 16. So let's deal with that due date, and then I'll let you guys work. Homework 11. What do we have as far as due dates are concerned? Looks like we've got Lab 9 due next week, so we can do next Friday. Looks like that one's open. So the 21st is when we'll have homework 11 due. All right. So I'll set that due date, but I think that's all that I wanted to record.